Hidden beneath these clouds is one of Earth's most difficult construction environments. Fragile limestone walls rise sharply above a valley thousands of feet below.
Welcome to the Apex Karst Viaduct. Today, we reveal how engineers designed 25
Our central case is the Apex Karst Viaduct, an advanced engineering concept.
Subscribe as we follow this structure from first survey to final operation.
The canyon compresses storms into powerful winds through a natural tunnel effect.
Karst limestone is fractured, soluble, and often weakened by hidden internal cavities.
Local fault movement adds earthquake forces to an already unstable geological system.
Large temperature swings continuously expand and contract every exposed structural component. Could engineers create a safe highway here without damaging this extraordinary landscape? The existing route follows unstable cliffs, sharp turns, and frequent landslide zones.
Even minor rockfalls can close the only regional supply route for hours.
A journey of only 30 miles can require nearly 5 dangerous hours. Farmers depend on this road to deliver fresh produce before markets close. Emergency vehicles face the same delays when minutes can determine survival.
Tourism remains restricted because visitors cannot safely reach the historic monasteries.
The new corridor must connect villages, markets, hospitals, and heritage destinations.
The project target is to reduce travel time to less than 1 hour.
Construction must avoid protected habitats and preserve the monastery without vibration damage. The finished route must remain safe during storms, earthquakes, fog, and heavy traffic.
Surveying begins with satellite elevation data covering the complete mountain corridor.
Specialized drones enter narrow valleys inaccessible to helicopters or ground survey teams.
High-density LiDAR records millions of points across the nearly vertical limestone walls. The point cloud reveals ledges, cracks, slopes, and possible foundation locations.
Engineers test multiple curves to control gradient within the restricted valley width.
Seismic sensors measure how sound waves travel through the limestone formation.
Reflected waves expose internal fractures, weak layers, and unknown underground voids.
Ultrasonic logging confirms the thickness and integrity of load-bearing rock zones.
Rock cores provide physical evidence of strength, porosity, and fracture orientation. Wind instruments capture extreme gusts where the future deck will cross. Weather records identify recurring crosswinds, turbulence zones, and near-zero visibility periods. The survey reveals enormous underground caverns beneath conventional foundation locations. Traditional vertical piles would transfer bridge loads directly into unstable hollow rock. Concentrated loading could fracture the cavern roof and trigger progressive settlement. A direct crossing creates a gradient too steep for trucks and buses.
Heavy vehicles would stall, overheat, or lose braking control during descent.
A conventional sweeping curve would destroy habitat and approach the monastery. A standard box girder would generate alternating vortices under canyon crosswinds. Repeated aerodynamic loading could produce dangerous torsional vibration in unfinished spans.
Seismic movement could force neighboring piers to respond differently during one event.
Untreated runoff could carry oil, tire residue, and sediment into karst ecosystems.
Low visibility requires automated lighting, speed management, and continuous traffic monitoring. Every acceptable route must solve 5 conflicting engineering constraints simultaneously. The solution must distribute loads, control wind, limit gradient, and preserve landscape. The team evaluates 4 structural systems against geology, wind, cost, and constructability.
A suspension bridge requires massive anchors in rock, unable to support them.
A large arch would demand temporary supports inside the inaccessible valley. A straight viaduct remains structurally possible but operationally unsafe for heavy traffic. The final design gains elevation gradually through multi-level spiraling viaducts. Inclined rock anchors transfer pier forces sideways into stronger internal limestone.
Deep bored piles bypass weak cavities and terminate inside competent rock.
A curved steel box girder reduces drag while resisting bending and torsion. Ultra-high-performance concrete creates stronger piers with smaller, lighter cross-sections.
Controlled super-elevation balances vehicle forces through the sharpest elevated curves.
Balanced cantilever construction removes most temporary support from the valley below. Mountain tunnels shorten exposed spans and connect the bridge to protected routes. Site preparation begins beyond the protected heritage buffer on stable ground. Earthwork remains inside surveyed limits to minimize permanent landscape disturbance.
A temporary microgrid powers cranes, workshops, pumps, sensors, and tunnel equipment.
A heavy construction cableway replaces roads unable to reach cliff foundations.
Proof loading verifies the cableway before structural modules enter the valley. Closed material systems keep dust and contaminated runoff away from forest.
High-strength netting captures falling stones before reaching workers or equipment.
Wind alarms stop lifting when canyon gusts exceed established safety limits.
Special tower cranes anchor directly into verified rock behind the cliff.
Tunnel refuges protect workers during storms, fires, or rockfall emergencies.
Move to the tunnel refuge. The safety team rehearses evacuation before major structural construction begins.
Corrosion-resistant steel arrives at the factory for box girder fabrication.
Each plate is inspected before entering the computer-controlled production line.
Laser cutting creates profiles required by the bridge's three-dimensional geometry. Programmable presses create controlled twisting for banked transition curves. Robotic welding maintains consistent penetration across thousands of structural connections. Controlled heat prevents welding distortion from changing the designed girder curvature.
Subscribe to follow every critical process behind this extraordinary engineering concept.
Laser scanners compare each module against millimeter-level digital tolerances. Radiographic inspection detects internal weld defects invisible from the surface. Approved welds remain permanently traceable through the project quality database.
Protective coatings resist moisture, salt-bearing fog, and long-term atmospheric corrosion.
Each rock anchor bundle is tested above its expected service force.
Ground assembly confirms geometry before modules separate for mountain transport. Oversized trailers deliver each module to the mountain cableway terminal. Construction begins with drilling platforms positioned directly against the limestone wall.
Deep boreholes pass weak surface layers and enter competent internal limestone.
Every borehole is inspected before accepting permanent structural load.
High-strength tendons are bonded using specially formulated expanding grout.
Hydraulic stressing locks each foundation block tightly against the mountain. Massive reinforcement cages distribute pier forces across verified foundation areas.
UHPC fills the foundation without exposing workers to the cliff edge.
Thermal monitoring prevents curing heat from producing internal foundation cracks.
Automated climbing formwork advances as each pier section gains strength. Balanced placement prevents uneven loading from shifting the slender pier.
Continuous surveying maintains alignment despite wind and daily temperature movement. Rotating form travelers prepare the first balanced cantilever deck segments. Reinforcement and pre-stressing ducts define each segment's final load path.
Twin segments are cast together to keep the pier continuously balanced.
Pre-stressing tendons connect each new segment to the completed cantilever. Hydraulic tension compresses the joints into one continuous structural beam. Curved factory-built modules arrive by cableway for tight spiral sections. Adjustable frames establish precise twist and super elevation before permanent connection.
Mechanical connections and pre-stressing integrate steel modules with the concrete deck.
Tunnel excavation advances through stronger rock behind the exposed cliffs.
Immediate ground support stabilizes fractured rock before permanent lining installation.
After years of construction, both sides approach the critical peak closure. During closure preparations, an unexpected storm enters the canyon bottleneck. Compressed airflow creates gusts stronger than earlier measurements predicted.
Without closure, the cantilever remains vulnerable to aerodynamic excitation. Vortices apply rhythmic forces near the structure's natural frequency.
Resonance amplifies movement faster than passive damping can suppress it.
Growing torsional motion threatens equipment, temporary connections, and personnel safety.
The safety system stops work and initiates emergency evacuation. Evacuate to the tunnel now!
Crews immobilize machinery before withdrawing through protected access routes.
All personnel reach refuge while the unfinished span remains exposed.
Closure work stops until engineers explain and control the vibration. Engineers synchronize structural movement with recorded wind pressure data. Data confirms vortex-induced resonance rather than foundation or material failure. Physical inspection confirms the storm caused no permanent structural damage. A revised wind tunnel model reproduces actual terrain and canyon microclimate. Flow visualization exposes strong alternating vortices along the outer girder edge. Multiple aerodynamic modifications are compared before changing the full-scale structure. Internal tuned mass dampers oppose the dangerous torsional frequency.
Open median panels reduce lift, while guide vanes disrupt vortex formation.
Artificial excitation measures how rapidly the redesigned system suppresses movement.
Measured damping exceeds requirements, allowing construction to safely continue. The peak closure module connects both sides into one continuous structure. Precision jacks correct thermal movement and establish final bridge geometry.
Continuous pre-stressing redistributes forces across the completed multi-level viaduct.
Adaptive lighting defines lane geometry when dense fog removes natural references.
Thousands of sensors create a permanent structural health monitoring network. Protected fiber links transmit structural and traffic data continuously. Variable signs automatically reduce vehicle speed during wind or fog. Flexible barriers distribute collision forces without overloading the bridge deck.
The drainage system captures contaminated runoff before reaching the karst forest.
Integrated tunnel systems complete a fully operational transportation corridor.
Final testing begins by recording unloaded geometry across every critical span.
Calibrated trucks create known forces for the static load test.
Maximum design loading concentrates where structural demand is greatest. Measured deflection remains within millimeters of the engineering prediction. Dynamic testing evaluates vibration, banking forces, bearings, and vehicle stability. Tuned mass dampers suppress motion before passengers could perceive discomfort.
Emergency braking confirms friction, barrier clearances, and safe stopping distance.
Artificial rain verifies tire grip and drainage under severe wet conditions.
Proceed to the marked exit.
A full emergency exercise tests detection, communication, ventilation, and rescue access.
Every structural, operational, and safety measurement exceeds required acceptance standards. Subscribe as the Apex Karst Viaduct begins official operation. Traffic gains elevation gradually, instead of climbing dangerous mountain switchbacks.
Automated lighting and speed control maintain visibility through dense cloud layers.
Reliable travel opens faster supply routes for farms, businesses, and hospitals.
The corridor expands tourism while preserving the monastery and mountain landscape.
Against impossible terrain, engineering connects people while respecting nature.